integration over x dash and integration over y dash are trivial, and they are giving us the result as 1. So what is left is integration over z dash. For integration over z dash, what we have is I z dash exponential j k z z dash. Now I z dash is equal to 0 beyond z is equal to L by 2 or beyond z is equal to minus L by 2. So if z is less than minus L by 2, I z dash is 0. If z is greater than L by 2, then I z dash is 0. So the integration limit for dz dash is from minus L by 2 to L by 2. So now radiation vector F will have only z component, as we have already seen. So F, since the current has only z component, so F will have only z component. So radiation vector F is equal to z cap Fz, that will be equal to z cap integration minus L by 2 to L by 2 I z dash exponential j k z z dash integration over z dash. So that will be radiation vector. Now the radiation vector depends on what? What are the factors on which radiation vector will depend? First thing is, we have last time saw that the radiation vector depends on the wave vector k, and the wave vector k in Cartesian coordinate system is given as k is equal to k r cap, that you can write as x cap kx plus y cap ky plus z cap kz. Why k r cap? Because k gives you the wave vector, and that is along the direction of propagation. Along the direction of propagation is along r cap, because the electromagnetic wave from the antenna propagates in the radial direction. Therefore, since it propagates along the radial direction, so it is always r cap. So k is equal to k r cap. Now what is kx, ky, kz in this case? As we already have seen when we discussed plane waves, we know what is kx. Kx is equal to k cos phi sin theta, ky is equal to k sin phi sin theta, and kz is equal to k cos theta. In our integration, we are not using kx or ky. We are using only kz, which is equal to k cos theta. So we will use only k cos theta, which means the integral is independent upon phi. Integral is dependent on theta, but kz does not contain the phi component, so integral is independent upon phi. A reason I have already told you, that it because of symmetry, current is along z direction, so xy plane is symmetric around the current, around the z axis. Therefore there will be no dependency on the phi. So radiation vector Fc depends on the polar angle theta only, it does not depend on the polar angle phi. So how we can write now? Fz theta is equal to integration minus L by 2 to L by 2 over dz dash of the integrand Iz dash exponential jkz z dash. That we can write as integration minus L by 2 to L by 2. Iz dash remains as it is, exponential j k, and because kz is equal to k cos theta, just put that. So exponential j k z dash cos theta dz dash. So this is what is the radiation vector dependence. Now what will be the components of this vector? Radiation vector components will be obtained from the components of the z cap, because f is equal to z cap into absolute of jf, so or magnitude of f. So f vector is equal to as the direction z cap. Now z cap, we know, if you decompose z cap, or if you look at the components of z cap in terms of theta and r cap. So z cap is in the Cartesian coordinate system. In the spherical coordinate system, if you find out the relationship between Cartesian coordinate system and spherical coordinate system, then z cap is equal to r cap cos theta minus theta cap sin theta. This we have already seen in the last class. Therefore, vector F is equal to z cap fz. That will be r cap fz cos theta minus theta cap fz sin theta. Okay. Now, we can see that F has two components. One component is radial because we have r cap fz cos theta. Other component is perpendicular to the radial direction. It is theta cap. So theta cap is perpendicular to the radial direction. So there are two components. One is radial, other is perpendicular. So the perpendicular component is equal to perpendicular component of F is, or we can decompose vector F into two components. One is the radial component Fr, other is the perpendicular component F perpendicular. So F perpendicular as a function of theta, which is the perpendicular component of the vector F. So the perpendicular component of vector F will be theta cap. It is along theta. So it will be theta cap F theta. So now compare this with F. So theta cap F theta is equal to minus theta cap Fz sin theta, from which we can say that F theta is equal to minus Fz theta sin theta. So F perpendicular is F theta and F theta is equal to minus Fz sin theta. Fz is a function of theta. Now, once we know the radial is the perpendicular component, the radial component is not contributing to the radiation. The radiation is always perpendicular, as I have told you in the beginning of the antenna. The radiation is always perpendicular to the direction of propagation. So if you have a component which is perpendicular to the radial component, that component is contributing to radiation. Therefore, F perpendicular is the component that is in which we are interested. That will give us the radiation fields. So let us find out the radiation fields. These radiation fields will be independent on the azimuthal angle phi. The reason is F perpendicular is independent upon phi. Therefore, this will be independent upon phi. They will be dependent on theta only. Okay. Now, if they are independent upon phi, which means they will be only confined to the xy plane. If they are in xy plane and they are equal everywhere, that type of field is called omnidirectional field. In one particular plane, it is equal at every point. That is called omnidirectional field. So our radiation fields are omnidirectional field. If it is omnidirectional, then we can say E, the electric field E, is equal to theta cap E theta. That will be theta cap j k eta exponential minus j k r by 4 pi r fz theta sin theta. This we have already seen earlier, this expression. Now also we have found out what is F perpendicular. E is equal to E cap E theta, and E theta, the variation, theta variation of E theta comes from F perpendicular, which is fz theta sin theta. The amplitude of E theta is jk eta exponential minus jkr by 4 pi r. So from that we get this E. Similarly, H is same as E except only one term, that is eta. You drop the eta. As you know, eta H is equal to E. Therefore, both are same. Only E is in the theta direction. H will be in the phi direction. That also we know. Why H will be in the phi direction, that you know. The current is along the z direction. Then using right hand rule, the magnetic field will be surrounding the current. So if it is surrounding the current, it will be in the xy plane. Since it will be in the xy plane completely, it will be in phi direction. It will be rotating in the xy plane, so it will have only phi direction. And why E will be in theta direction? because E is perpendicular to H and E is not in the propagating direction, or E has no R component. So therefore E will have theta component, E theta cap, E theta. Okay. And then in these two expressions, if you look at the expressions for E and H, there is a factor sine theta. What is the source of this factor sine theta? The source of this factor sine theta is the transformation of the coordinate system from Cartesian to spherical coordinate system transformation. That gives you the that gives you the sine theta. So from that we get the sine theta. Now we have to find out what is the factor fz theta. That is more important. The factor fz theta, this actually incorporates the dependence of the assumed current distribution Iz. All other things we have already discussed earlier, so they come from that. So only fz theta, that will depend on the current distribution. Now let us find out the radiation intensity. Once we know this, let us find out the radiation intensity. Radiation intensity we defined as U, and U depends on theta and phi, that we have already seen. So U theta phi is the radiation intensity. Now we know that the radiation intensity depends on the electric field and magnetic field of the power, but the radiation intensity depends on power. Power comes from electric field and magnetic field, both of which are independent upon phi. Therefore, power is dependent only on theta. If power is dependent only on theta, then U theta phi will be dependent only on theta. So radiation intensity has a theta dependency only. It has only a theta dependency. Now we define the Poynting vector. Sometimes we write it as P, sometimes you write it as S. In electromagnetics, it is written as mostly S. In antenna, mostly people write it as P. Both are same thing. So the Poynting vector gives you the power density. So the power density is equal to half a real part of E cross H conjugate. So that is the definition of our Poynting vector. Time average Poynting vector is given by this expression. Now put what is E. We have found out what is E. E is equal to jk eta exponential minus jkr by 4 pi r. Then that into fz. Similarly, H is equal to jk exponential minus jkr by 4 pi r into fz. Now the H star will be therefore jk into exponential jkr by 4 pi r. So use those values. If we use those values, and for f we have fz has two components, f theta and f phi. So E will be theta cap f theta plus phi cap f phi. Then H star will be phi cap f theta star minus theta cap f phi star. So just multiply that part. This the part that I have highlighted, real theta cap f theta plus phi cap f phi cross phi cap f theta star minus theta cap f phi star. If you multiply that, that will give us theta cap cross phi cap is equal to r cap, or phi cap cross theta cap cross minus theta cap, that gives you r cap. Therefore, that will give us r cap into f theta absolute square plus f phi absolute square. And how we know that E cross H star will ultimately, that comes from f perpendicular. Therefore, that we can write as r cap f absolute f perpendicular square. Now this is written as f perpendicular theta phi. This is the general expression, but it is independent upon phi, so we can write f perpendicular theta absolute f perpendicular theta square. That is also correct. Now what is this f perpendicular f theta phi? That you can write simply as f perpendicular theta phi square absolute square is equal to f theta phi absolute square plus F phi theta phi square, absolute square. So using this expression, now the P or the density becomes R cap PR is equal to, now multiply these things, the highlighted portion is absolute F theta phi square, so that is the last term, then R cap remains as it is. Then what are the other terms? Minus jk eta into jk, so that is k square eta. So k square eta is in the numerator. Then exponential minus jkr, exponential jkr, that is 1. So numerator, that 1 is gone. Then in the denominator you have 2 into 4 pi r into 4 pi r. So that gives you 32 pi square r square. So P, which is equal to r cap PR, is equal to r cap eta k square by 32 pi square r square, then absolute of a perpendicular theta p square. Okay. Now this P gives you, the Poynting vector gives us the power density of radiation. So radiated field, what is the density? That is given by this Poynting vector. So the power density, suppose the power is dP, is intercepted by an area element ds. So the antenna is radiating power. You consider a large sphere at a large distance. Antenna is at the center of the sphere. Radius is very large. At a large distance, we are considering a sphere. On the surface of the sphere, let us consider an elemental area ds, and the power over that elemental area is dP. So that is what we are considering. So then dP by ds will be equal to, and dP of ds will be equal to dP, then ds, this area, elemental area, if that subtends an angle and d omega, a solid angle d omega at the center or on the antenna, then this ds is equal to r square d omega. So dP by r square d omega, now that will be equal to PR, power density. dP by ds gives the power density. Power density is defined by this. So PR is equal to dP by ds. We have found out expression for PR. The expression is eta k square by 32 pi square r square into absolute a perpendicular square. Now if I compare this expression with dP by r square d omega, then r square from both the sides, right hand side, left hand side, they will cancel out, leaving me dP by d omega. By definition, radiation intensity is dP by d omega. Therefore we find out the radiation intensity, which is dP by d omega, or the power radiated per unit solid angle. So U theta phi is equal to dP by d omega. That will be equal to r square into PR, or that will be equal to eta k square by 32 pi square, a perpendicular square. So that will be U theta phi square. So let us rewrite that. F perpendicular for a linear antenna is equal to Fz theta square. F perpendicular is Fz sin theta. So if I put that Fz sin theta, then U theta phi is equal to eta k square by 32 pi square remains as it is, Fz theta square into sin square theta. So U theta phi varies like this. Now once we are equipped with this, let us consider a Hertzian dipole. What is a Hertzian dipole? Hertzian dipole is an antenna which is actually a fictitious dipole, but in technology, in engineering, we call an antenna to be a Hertzian dipole, a linear antenna to be a Hertzian dipole if its extension is less than lambda by 50. So the Hertzian dipole, for Hertzian dipole, L is less than lambda by 50. Extension of the dipole is L. So L is less than lambda by 50. Lambda is the wavelength. So 150 is 1/50th of the wavelength or less than that is in engineering or technology termed as Hertzian dipole. So now for the Hertzian dipole, Fz is equal to minus L by 2 to L by 2 Iz dash exponential jkz z dash dz dash, that we already have seen this expression. Now what is Iz dash for a Hertzian dipole? We have seen the different current distributions for the linear antenna. Iz dash is IL delta Z. So put that IL delta Z, and exponential kz z dash is exponential j k and z dash cos theta. So that into dz. Now if you use the Dirac delta function and its property, then this integration will give us I into L. So Fz is equal to IL for a Hertzian dipole. If Fz is equal to IL, then intensity U is equal to eta k square by 32 pi square into Fz square sin square theta. Fz is IL, so IL square sin square theta absolute. Then what will be maximum value of this U theta? The maximum value of intensity, that will be when sin square theta is equal to 1, because everything else is constant. N, eta, k, 32 pi, IL, everything is constant. So what is varying is theta, sin square theta. Sin square theta minimum value is 0, maximum value is 1. So maximum Umax will be eta k square by 32 pi square IL square. So once that is defined, then we define something called a normalized power gain. So normalized power gain actually is G theta, that is the intensity by maximum intensity. So what we do in normalized power gain is we normalize the amplitude of the intensity to 1. So G theta will be U theta by U max, that is equal to sin square theta. Now you remember this beam solid angle, this we have defined delta omega, that is surface integral of theta over 0 to pi and phi over 0 to 2 pi of the term G theta sin theta. So if we define that integration, the integrand is is dependent only on theta, therefore it is independent upon phi. So the integration 0 to 2 pi d phi will give us 2 pi. So that 2 pi will become outside. So inside will be 0 to pi G theta sin theta d theta. G theta is equal to sin square theta for a Hertzian dipole. So put that gives us sin q theta d theta integration from 0 to pi. So that you can do easily, integrate that will give us 8 pi by 3. So now once we know what is beam solid angle, we can find out what is the directivity of the antenna. The directivity of the antenna D max is equal to 4 pi by delta omega or 4 pi by beam solid angle. That is the directivity. So that you can find out 4 pi by 8 pi by 3, that is actually 3 into 4 by 8, which is 3 by 2, which is equal to 1.5. So directivity is 1.5. If we express that in terms of dB, so take 10 log 10 of 1.5, that will give you 1.76 dB. So directivity is 1.76 dB. Now let us come to the radiated power of the Hertzian dipole. So power radiated P rad is equal to Umax into delta omega. As you know, Umax is given as P rad by delta omega. So from that we can get radiated power is equal to Umax into delta omega. Now P rad we can write eta k square by 32 pi square for Umax, and that into IL square, IL absolute square. Then delta omega is 8 pi by 3, and so put all those things. If we put everything, and undo the algebra, that will give us eta k square il square by 12 pi. That we can write as 1 by 2 r rad into I square. Well, because we have got a term I square in the expression, so except I square, take everything else as r rad. Why we are taking this? Because we know power, power is given by time average power is given as 1 by 2 times r into I square. So everything if we took together except I square and 1 by 2, so whatever left is r rad. So r rad is equal to eta k square L square by 6 pi. What does this signify? The power is radiated. Since this is radiated power, suppose we replace the antenna by a resistor. If we replace the antenna by a resistor which will consume the same amount of power as the power radiated by the antenna, then the resistance of that power is r rad. That resistor is r rad. That is why it is called radiation resistance. R rad is called radiation resistance. It is a fictitious resistance, and if you put a resistance of this value, then that will consume the power that would have been radiated otherwise radiated by the antenna. Therefore, r rad is equal to eta k square L square by 6 pi. Then you know what is k. K is equal to 2 pi by lambda. So if you put k is equal to 2 pi by lambda, k square will become 4 pi square by lambda square. So that will become eta into 4 pi square by 6 pi into L square by lambda square. So on that we can write as 2 pi eta by 3 into L by lambda square. Now 2 pi eta by 3 is 2 pi, eta is equal to 120 pi. So put that, so 2 pi into 120 pi by 3. So that will give us approximately 789 into L by lambda square. Now if you look at this, the significance is, suppose we take 789, let us approximate it as 800. L by lambda, let us take, as we are considering Hertzian dipole, so L by lambda should be less than, L by lambda should be less than, L should be less than lambda by 50. So L by lambda should be less than 1 by 50. Now let us take L by lambda is equal to 100. If we take L by lambda is equal to 100, is equal to 1 by 100, then that is less than 1 by 50, so that is okay. 1 by 100 is 0.01. So 0.01 square. 0.01 square is 0.0001. So multiply that with 789, that will give you a very small value. So r rad is a very small value. If r rad is very small, if you have a small resistance, it will not consume more power, which means less power will be consumed, antenna will radiate very less power. So if you have a small, like a Hertzian dipole, it is an inefficient radiator. Now why we call it Hertzian dipole instead of Hertzian dipole? Many times we people call it in technology or in engineering, this is called a finite Hertzian. So it is not infinitesimally small, so it has a finite length, so it is called a finite Hertzian or a uniform line element. If it is a uniform line element or a finite Hertzian, this is called a small antenna. A small antenna actually is something between a Hertzian dipole and a small antenna, that is the length L should be less than lambda by 10, but it should be greater than lambda by 50. So if the length is less than lambda by 10 and greater than lambda by 50, it is called a uniform line element or a small antenna. Now for the Hertzian dipole, Iz is equal to, or finite Hertzian dipole, Iz current is equal to I into uz plus L by 2 minus uz minus L by 2. Now what is u I am sure you have read this in network analysis by this time or in any other course. U is called unit step function. So uz is equal to 0 if z is less than 0. uz is equal to 1 if z is greater than 1. So if you look at uz plus L by 2, that will be 0 if z plus L by 2 is less than 0 or z is less than minus L by 2. So in that range it is 0. So beyond that it is 1 up to infinity. From that you are subtracting uz minus L by 2. So that will be 0 everywhere if z minus L by 2 is less than 0 or z is less than L by 2. But it will be 1 if it is greater than L by 2. Which means uz plus L by 2 minus uz L minus L by 2 will be 1 in the range minus L by 2 to L by 2. So Iz will be 1 over that range, that small range. Now let us write Iz in this form. Multiply in the numerator L, denominator L. So if you multiply L in the numerator and denominator, then Iz is equal to IL into uz plus L by 2 minus uz minus L by 2 divided by L. L is extremely small, so L will be, we can approximate as delta Z. So then uz plus L by 2 minus uz minus L by 2 by delta L, or that is actually du by dz. So Iz is equal to IL du by dz, and on differentiation of unit step function gives us a delta function. That is a property of unit step function. Differentiation of unit step function gives us a delta function. So that is called to IL delta Z. So IL delta Z also we can write in this manner, instead in form of a unit step function. So now since we completed our discussion on RG and dipole, we'll take a break and we'll come back in 5 minutes and start discussing about other antennas.